In this lecture, we will continue the alteration method. So, I hope you remember the basic idea of the method. We had summarized this at the end of the last lecture. Okay. So, the setup is almost the same as when we were using the expectation method. We are trying to prove the existence of an object with a numeric parameter lower bounded or upper bounded by a certain value. Okay. That's the that's the setting under which we are working. In the normal expectation method, we would try to design a random experiment which will whose sample space will contain the objects of our interest, and then we try to estimate the expected value of this numeric parameter. In order to do that, we had to design the experiment in such a way that it is easy to break down the random variable as a sum of easy to compute indicator random variables and so on. That part remains the same, but the key difference is that we are a bit more lenient with the experiment design, in the sense that when we the output of this random experiment need not always throw objects which satisfy all the requirements that we have. We are allowed to do some minor alterations later on, and these alterations also you have to quantify in terms of a random variable, find the expectation of that random variable also, and then add or subtract it to the original one based on what kind of alteration it is. So yeah, it's a very clever idea, but in some sense it's very similar to the expectation method. This is also considered a first moment method because expectation is a first moment of a random variable. Okay. Now, this third example that I have chosen goes back to the examples that we started from the beginning, okay, on Ramsey numbers. Recall the definition of R of k. R of k was the smallest natural number n, okay, such that if you take a complete graph on n vertices and color its edges using two colors in any way, okay, not necessarily randomly by a coin toss or anything. So the statement is deterministic, or the definition is deterministic. You take a complete graph on n vertices. There are n choose 2 edges. Each edge you can color in whichever way you want, but using two colors. So let's say red and blue. The claim is that then no matter what is the coloring, you will get a monochromatic click on k vertices, which means k vertices such that all the k choose 2 edges which are between them, induced by them, will be of the same color, either all red or all blue, right? That was a definition of R of k. Okay, and it's easy to see that it's a monotonic parameter in the sense that if Rk is some 1000, then for 1001 click or 1002 click also the same thing happens. Okay, so that's why we are looking for the minimum, the smallest natural number n, which has this property. We saw an upper bound of 4 to the power k and a lower bound of root 2 to the power k, okay, or equivalently an upper bound of 2 to the power 2k and a lower bound of 2 to the power half k. And using the alteration method now, we will improve this lower bound. Remember, the lower bound was where we used the random construction. Again, the idea was simple. You color each edge uniformly at random independently, and then analyze the probability that there is a bad event. There is at least one monochromatic click. Pick your n such that this probability is less than 1. If this probability is strictly less than 1, then you are done. Since the probability of a bad event, something bad happening is less than 1, the probability of something good happening is greater than 0, which can only happen if there exists at least one good object, which means an object without a monochromatic k click. That was the idea. Today, using the alteration method, we will add a k factor to the lower bound. I mean, this quantitatively speaking, adding this k factor is not significant, okay, because you are adding a linear term to an exponential growing term. So order wise, this does not play much of a role. Okay, so this is also in the spirit of illustrating the power of a technique, or more precisely in this case, to compare the power of this alteration method with the previous methods that we are doing this. Okay, now what is the technical, or this omega? This expression comes after some amount of arithmetic manipulations, but before that, this is the starting point. So I want you to pay close attention to this formula. Okay, so this is the technical claim. So there are two things for us to do now. First is to prove this lower bound, and then to show that from this lower bound, using some optimization for n, we will get this bound. Okay, so this lower bound, as is written here, is valid for any n. Okay, So let me read it out, and maybe with my emphasis, I'm trying to give a hint. Okay, we are saying that, remember that this is a proof by alteration method. So we are saying that for any natural number n, okay, you pick any natural number n, then n minus this number here, okay, is a lower bound for R of k. Okay, so think of n as a large number, which is the kn that you will start with, number of vertices of the complete graph that you will start with. Now, if that is the kn, then what is this red quantity that you are subtracting out? This is, you can think of it two ways. You can argue it using the union bound also, but I'm planning to say this in terms of expectations. This is the expected number of monochromatic k clicks that you get if you do a independent and uniformly at random 2 coloring of the edges of k. Okay, it's a long sentence, but I think by now you are very familiar with this procedure, right? So you start with this complete graph on n vertices. There are n choose 2 edges. Each of them you color uniformly and independently with probability half, either red or blue. And then you calculate the expected number of monochromatic k clicks. Okay, the probability that one k click is monochromatic is this number, 2 to the power minus k choose 2 multiplied by 2 because of either it can be all red or all blue. N choose k is the total number of possible k clicks, right? And by linearity of expectation, you can model this as a sum of indicator random variables. This is the expected number of clicks. Okay. Now, can you guess what is the alteration? Yeah, I think it should be obvious by now. You can take this complete graph kn, do this random coloring, and from each monochromatic k click, okay, not from every k click, each monochromatic k click, delete at least one vertex. Okay, this is the same way that we did for finding independent set, right? We picked a set at random. If an edge got trapped in the set you picked, you deleted one endpoint of that edge. Similarly, if you, after the coloring, if you did not get what you wanted was a coloring in which there was no monochromatic k clicks, but if you got some, then from each of the monochromatic k click, you have to delete at least one vertex, which means at most you will be deleting this number of vertices on expectation. Okay, on expectation, this is the number of vertices that you delete. Okay, so hence this claim. Okay, or how do you argue out in a bit more of a detail? So since it's a random experiment with this expectation, there exists at least one coloring in which the number of monochromatic k clicks is at most this much. You take that coloring and delete at most these many vertices from n. You will be left with n minus n choose k2 to the power 1 minus k choose 2 vertices. And what about that complete graph now? It's a 2-colored complete graph with no monochromatic kn, right? And that serves as a lower bound to Rk, right? Because Rk is the smallest. Yeah, in fact, that serves as a strict lower bound to Rk, because Rk is the smallest number where any coloring results in a monochromatic k click. We have now exhibited this altered graph where there is no monochromatic k click, and hence your R of k has to be strictly larger than that. That's the idea. Okay. Now, the next step is to go from this expression to what we want, which is a maximization over n. Okay, yeah. So, this is the description of what I already told, and I don't want to repeat that. The same, independent uniform coloring, number of monochromatic k's is your random variable. Its expectation is that term that you are subtracting out. Let me call that beta. I want to use this beta because I again want to go and maximize that. Yeah, and this expectation calculation is here. There is a coloring with at most beta. So I think I have said all of this. The remaining graph, pick that coloring and delete one vertex from each of the monochromatic k's. What is the remaining graph? First of all, it's a 2-edge colored k n prime, where n prime is this n minus, at least n minus beta. Sometimes deleting one vertex may kill more than one monochromatic k clicks if they have a common vertices. Hence, this is a bound. But the key property is that once you finish all these deletion, there is no monochromatic k left. Okay. Now, we need to do the second step. Okay. So, we want to find the best n so that this n minus this function is as large as possible. We want to differentiate it with respect to n and set it to 0. But in order to differentiate a combinatorial function, like this n choose k and so on, it is easier to give it an upper bound and then differentiate, right? Remember, we are looking for a lower bound for rk, so this comes as a minus thing. So you are allowed to subtract a upper bound for this quantity n choose k 2 to the power n minus k. And this is the standard upper bound for n choose k, en by k the whole power k. Okay, we have used this before also, that any n choose k can be upper bounded by en by k to the power k. Okay, now this is more easy to differentiate. What would be dou beta by dou n? K en power k minus 1, this e over k will come here, 2 to the power 1 minus k by 2. And to find the, we said this, to find the best n, we should not set the differential of beta to 0, we should set the derivative of n minus beta to 0. Okay, so there is a 1 minus this derivative here that is coming here. You rearrange the terms and you see that approximately what you get is something like this, en by k minus en to the power k minus 1. This k minus 1 and this k minus 1 would have gone off if this 1 by 2e was not there. Okay, but now this differentiating and setting it to 0 is to find the best point. When it is okay, even if you don't pinpoint that best point, you are allowed to do all these approximations, because at the end of the day, whatever point at which, whatever n we will pick, we will have to substitute back then, and what we get is the bound that we will report. So when you are doing these approximations, you are not making a mistake when you are finding the optimum point. It's okay if it's not the exact optimum, but it is this way or that way. There will be nothing wrong in the proof, but you can still worry that maybe if you had spent a bit more of calculus time and did this optimization more, then you would have ended up with a better solution. That's likely. I'm not ruling that possibility out, but for simplicity, I'm just ignoring this constant for a moment. And then I can cancel out this k minus 1 from the exponent, and I get en power k is approximately 2 to the power k by 2, or n is approximately k by e to the power 2k by 2. Okay, but this does not say that this n is the lower bound. Remember, the lower bound is n minus beta. Okay, so this gives the n that will maximize n minus beta, but we still have to find out what is n minus beta. So what would be n minus beta? N minus this guy here. Now substitute for n this value, and here also you have to do that substitution. But okay, en by k, if you look one step before, is nothing but 2 to the power k. So this is 2 to the power k squared by 2. Okay, so again I am doing some manipulation here. Direct. You should rather actually pause and complete this yourself. So you will get something like k 2 to the power k by 2 by e. This was the e term. The term that you are subtracting out is of the order 2 by k times the first term. Okay, so what you are subtracting out is of the order 2 to the power k by 2, which is more like a 1 by k factor of the n term, right? So usually if you start with some n, what you are subtracting out is approximately n by k. So you are almost left with n times 1 minus 1 by k, which is close to n. Okay, you are only deleting. Think about k as like 5 or larger. Okay, so this gives you this omega k to the omega k times 2 to the power k by 2 bound, which we had promised. Okay, this is the bound that we had promised in the theorem. Okay, now you may. Okay, I do not know the next discussion, but I think I have time, so let me quickly tell as to why you would have got this improvement by a multiplicative factor of k. Okay, in fact, the same problem, finding a lower bound for r of k, we can attack it using all the three methods that we have learned so far. Okay, the basic method we already saw, where you every time the coloring of the edges is it is a random two coloring, independent and uniformly at random. There you estimated the probability of a monochromatic existence of a monochromatic clique using union bound, which gave you this expression, and we said that okay, and this expression is a polynomial in n and exponentially going down nk. So there is some value of n till which this is greater than 1. Okay. It remains greater than 1. Remember that this is an increasing function of n. If you plot this function with n, I have plotted it below, it would go something like this, right? It's almost like n to the power k. So if I am plotting this function as n as the x-axis, it will go like this k to the powers graph like this. And which n do you fix? You look at where is your 1, right? And then that value of n, which is largest but still below 1, is what you will pick as your lower bound for r of k. All right, solve for n in terms of k. This is what we want. If as long as this is strictly less than 1, our probabilistic argument or reasoning will work, and we conclude that r of k is greater than. Actually, you could have done the same thing using expectations also. The same random experiment, no change here. Now x you set as a random variable which counts the number of, okay, this counting is the new idea here. It counts the number of monochromatic KKs. Now the expected count is this guy, which we know. We have seen it already using linearity of expectation. This linearity of expectation now replaces the role of union bound. They are different things, but sometimes when you are adding up indicator random variables and all, the expression seems the same. Okay, but still don't get confused with equating one to the other directly. And now we can claim that if this expected number of clicks is less than 1, now if the expectation of certain quantities is Ex, surely there exists one outcome in the sample space where the x value is less than or equal to Ex, which would mean it is less than 1. But remember, this is a count, and hence less than 1 means it's 0. Okay, because this is a counting random variable, its range is 0, 1, 2, 3, etc. So less than 1 would mean 0. So if Ex is less than 1, then there is no monochromatic click for this size, hence your Rk has to be larger than that. So this is a different philosophy, but the same result. We did not get any quantitative improvement. We got probably an alternate viewpoint to the same proof. But when it comes to the alteration method, the method we already saw, it's the same coloring plus this extra step of removing one vertex from each monochromatic k. And now let's say what is y, the number of vertices which have to be removed. This can be upper bounded by number of monochromatic KKs, because in order to kill every by the way, if you got confused, suppose instead of a monochromatic KK, your random coloring threw a monochromatic KK plus 1. Then you may wonder whether deleting one vertex will be enough. But within this monochromatic KK plus 1, your count for number of monochromatic KKs will be K. Okay, because in fact k plus 1, removing each vertex will still leave a monochromatic KK. So in fact you have enough budget to delete k plus 1 vertices from such clicks. Okay, so that's not a problem. But anyway, that's a minor side point. The thing is that the alterations that we wanted to do, the number of vertices which we want to remove, can be upper bounded by this random variable that we were analyzing in the previous method, the number of monochromatic KKs. Hence your Ey is at most Ex, which is this quantity we have calculated, and your Rk by our earlier argument comes to this. But now why does this expression here give a better bound than this expression here? Okay, so why here also you are trying to, in the first two methods you are trying to maximize this guy, find the maximum n so that this guy is still less than 1. That was the best lower bound you could get. You wanted to maximize this highlighted expression, find the, sorry, not maximize highlighted expression, I am saying the same mistake twice. Find the largest n so that this expression here is still less than 1. That was what we did. But in the third method, in the alteration method, we are trying to take this whole expression now together with this n minus and just maximizing it. Okay, we don't want this to be less than 1. Okay, but now remember, in that range where the first two methods worked, where this was less than 1, you could have still got n minus, let's say this was some 0.9, you could still get Rk is greater than n minus 0.9, which would mean Rk is greater than or equal to n, right? Because Rk is also an integer value. Okay, so this method in some sense already sees that our optimization trick that we did for the first two methods is one possibility under this which would give you a bound like n minus 1. But the benefit of this method is that here you can run n a bit longer, so that maybe this may grow above 1. It is still okay provided the n that you gain is more than this factor's gain. Okay, I have tried to draw the pictures for the case when k equal to 5. Okay, so I'm plotting two functions, n choose 5, 2 to the power 1 minus 5 choose 2. So 2 to the power 1 minus 10, 2 to the power minus 9. That's my first function. And the second function is n minus that function. Okay, and I have tried to plot roughly both these functions here. The green is the first function which keeps on increasing like the fifth power of n. The x-axis is n and the y-axis is these two functions. Whereas the second function, for small values of n, the first term dominates. It grows like a linear in n. Remember that somehow this vertical scale is shrinked corresponding to the horizontal scale. It grows almost linearly. After a point, this guy starts to take over and then it brings it back down. In fact, this will continue. This will actually continue going to negative after a while. So in the first two methods, you were essentially looking at the green curve, waiting for the maximum n so that it is still below this 1 and then reporting that value as the lower bound for R of k. In this third alteration method, you allow it to run bit higher. That's okay, but you are now not analyzing this alone, but you are analyzing its difference from n, right? And that will peak at some point, and then you can take that peak to be the n value that report. Okay, so in this picture, like n equal to k equal to 5 and all, this difference doesn't seem very significant because the omega notations, constants and all will kind of bury it. But I kind of generated this plot first using Wolfram alpha and then tried to sketch it out here. You could for instead of 5, if you put a large number like 500 or so, you will see that the difference is more pronounced. Okay, so that's the alteration method and what improvement it gives to the Ramsey lower bound. Okay, I wanted to continue with this Ramsey lower bound for the off diagonal case also. I'll tell you what is the off diagonal case first, and then in fact here the difference between the normal method and the alteration method will be more pronounced. Okay, so far in a two coloring of a complete graph Kn, we were looking for a coloring which neither has a red, let's say K10, or a blue K10. But why did it have to be K10? Why did it have to be 10 for both red and blue? Okay, so maybe I am okay to tolerate a K10 and a red K10 and a blue K20. Can we allow these two guys to be different? And yeah, why not? Okay, it's only a mathematical definition. So let's define the off diagonal Ramsey numbers this way: R of k comma L. Okay, so our standard two colors will be red and green. Okay, not blue. I was speaking blue, so let's say red and green. K will indicate the red color as here. Okay, so RKL is again the smallest natural number n, such that any two coloring of the edges of Kn will leave what? Any two coloring of the edges of Kn will leave either a red KK, that's a monochromatic KK, but not just monochromatic, it's of the first color, or it will leave a KL of the second color. Okay, that's the idea. So yeah, before going into the exercise, let me ask a simple question. So what would be, let us say, R of 5 comma 2? Okay, so you want to find the smallest natural number n, okay, the smallest natural number n, such that any two coloring of this Kn should leave either a K5 which is red or a K2 which is blue. Now this K2 which is, green, this K2 which is green is the easier guy to analyze, right? K2 is just an edge, right? So even if you color a single edge with green, you get a green K2, right? Which means if this coloring has to satisfy this property, then you cannot use any green edge at all, which means your entire click would be a monochromatic red click, right? Hence this number is nothing but K5, right? This is the smallest number because anything, if you have 5 or higher, if you use even one green edge, then the K2, green K2 is satisfied. Otherwise, the red K5 is satisfied. You know that it cannot be 4 because then you can color all the edges with red and none of this will happen. So, or I could have in fact said Rk comma 2 is equal to K for all K. In fact, this is a symmetric function. This will also turn out to be K. Okay. The role of the colors can be easily reversed. Yeah. So now what is, this is an exercise for you to show an upper bound. I'll give you a hint for this exercise, and this will give an alternate proof for the upper bound for diagonal Ramsey numbers also. The Ramsey numbers that we have seen are called diagonal Ramsey numbers, which are obtained when K and L are the same number. Okay. But when you when you generalize our study to off-diagonal Ramsey numbers, actually there is a very cute upper bound argument that comes up. Okay, we can upper bound RKL by the sum of RK minus 1L and RKL minus 1. Now this is the idea. In order to show that this is an upper bound here, we have to argue that any graph on n which is equal to this Rk minus 1L plus Rkl minus 1 vertices, if you take, will contain, if you take this as your n and do any two coloring, it will contain either a kk in red or a kl in green. The argument is, first you apply you pick the first vertex v1, so there are remaining n minus 1 neighbors to v1. Group them into, based on the color of that edge, you group them into the red bucket and the green bucket, right? Now, if the red bucket has this many, okay, Rk minus 1 comma L or more vertices, you are done. Because if you have this or more vertices, you either in any two coloring, which is in this case the coloring that is induced, the coloring is done for the whole graph. That coloring in particular will either have a monochromatic kk minus 1, a red kk minus 1, or a green L. If you got a green L, then you are done directly, right? Because the whole demand is only for a green KL. You are done directly. But if what you get is a red kk minus 1, then you include this V1 also to it to get a red RK, red KK, right? That way the demand will be met. Similarly, in the green bucket, if you have this size or more, RK L minus 1 or more, if you get either you get a red KK or a green KL minus 1. If you get a red KK, there itself you are done. If you get a green KL minus 1, together with V1, you get a green KL, and therefore you are done. Okay, now my pigeonhole principle, if you have n minus 1 vertices here, if this n1 is strictly, if n1 is strictly less than this, and n2 is strictly less than Rk L minus 1, that means n1 plus n2 is strictly less than n minus 2, right? Because this number is n, so this is, less than or equal to n minus 2, and which is a contradiction because n1 plus n2 has to be n minus 1. Okay, it cannot be strictly less than n minus 2. Okay, so I told it's an exercise, but I think I gave the whole proof. But I did it fast, I know. Okay, now from this you can easily verify that R3, we already know that R3 is 6, okay, and if you apply this, you can bound R33 by R23 plus R32. R23, we just observe that any RK2 and R2Ks both are just K, right? So R32 is 3, R23 is also a 3, adding up you will get 6. Okay, so you get the same bound. This is not surprising. This is in some sense the cleanest generalization of the R3's upper bound pigeonhole principle argument. Okay, when we did it in the first or the second lecture, we went through a more complicated route because we were only analyzing diagonal Ramsey numbers. So actually using off diagonal Ramsey numbers, the proofs become quite tricky. Quite more simple and more elegant. Okay. Now I can, once you have R33 and R24, you can calculate R34, which happens to be 10. Actually here I'll there is a very nice exercise to show that R34 is actually less than or equal to 9, and this is by parity argument about we know that you cannot have an odd degree, a graph with odd number of vertices and every degree being odd. Okay, so using that you can say that you can rule out the possibility of 10 and you will get you will get an upper bound of 9. Continuing, for R4 4 you have to add R3 4 and R4 3, which will give you an upper bound of 20. In fact, by this process, if you even find R5 5, the next will be R4 5, which will be 20 plus 10 30. R5 4 will also be 30. So R5 5 will be then 30 plus 20, right? So 5 4 plus 4 5, no, 30 plus 30 will be 60. 45 is the best known bound. Okay, so this method is not that bad, and you can actually generalize. If you see what is the formula, this turns out to be RKL is K minus 1 plus L minus 1, choose the first or the second. Okay, you can the choose whatever you can write, either K minus 1 or L minus 1. Okay, or K plus L minus 2, choose K minus. This you can prove by induction using the base case as your, this you can, this is also an exercise. Prove by induction. The base case is R of K comma 2 and R of L comma 2. You can even take K comma 1 and L comma 1 as the base case and apply this formula, but conceptually this is simpler. Okay. Then what is, now if you substitute K equal to L, that's a diagonal, guys. You get this 2 K minus 1 plus K minus 1. 2K minus 2, choose K minus 1, which is upper bounded by, this is a middle binomial coefficient in the expansion of 1 plus x to the power K minus 1 plus x to the power 2K minus 2. Okay, so this is, this is not 4 to the power 2K minus 2. This is 2 to the power 2K minus 2. Again, approximately 4 to the power K. There is a 1/4 coming here, but you could reduce the, you could put a root K, extra root K in the denominator. Okay, so remember our alteration method in the lower bound gave a improvement of a multiplication factor of K. This method gives an improvement in the upper bound, which is a multiplication factor of 1 by root K. Okay. But now, so this is the off diagonal numbers. I hope you have appreciated the definition. With that, last problem for this class is to show that among all the among Ramsey numbers, the diagonal ones are the most popular by far. But among off-diagonal Ramsey number, the most popular is the most off among the off diagonals, right? Which is that R3 comma L. Okay, so this is the smallest n for which there exists a 2 coloring with no red K3, no red triangle and no monochromatic KL. Okay, so this is very popular because actually instead of thinking the edges as colored using 2 colors, red and green, you can also think of the edges as the red edges being present and the green edges being deleted, or vice versa, both are working, right? So in that model, we are saying this is the smallest triangle free graph, okay, because the red edges are staying and hence no red triangle would mean the remaining graph where only the red edges survive is triangle free. Okay, so this is the smallest triangle free graph with, now what does a monochromatic green KL correspond to? What does a green KL correspond to? All the edges are deleted, green edges are deleted, right? So this green KL will correspond to an independent set of size L. So this also, this R3L is the smallest natural number n such that there exists a triangle free graph on n vertices, triangle free graph on n vertices with, what is its independent number? There is no green KL, which means once you delete the, you are only deleting the green edges, which means there is no independent set of size L. So alpha G is strictly less than L. Okay. So for example, we will come back to this sometime more, but this is one reason why this R3L is very popular because triangle free graphs are a very well studied, very useful and very well studied class of graphs. Okay, and this gives an upper bound on the independence number of triangle free graphs. Okay, now let's try to prove this claim. Here the calculus is far more complicated than what we did earlier, but the idea is exactly the same. Okay, and here the only difference in the idea is that we won't go for a uniform coloring. We will go for a coloring which is still independent, but there is a parameter p. With probability p we color it red, and with probability 1 minus p we color it. With probability p we color it red, and 1 minus p we color it green. Now this is not surprising because now the sizes of the red and the green clicks that we are targeting are different. Hence it's natural that the probability p may be different, and we will fix this p only later, not now. Okay, now this idea I want you to just stare at this line and understand it. Okay, so I am claiming that R of 3 comma L is lower bounded for any n. This expression is true, and any p that you can, any valid probability that you can choose, n minus the number of monochromatic, this n choose 3p cube. And so this number here you should be able to recognize it immediately as the expected number of red k3s, and this quantity here, this expression, you should realize it quickly as the expected number of green KLs. Okay, so and now this is a alteration method or a double alteration method. You start with Kn, independent coloring with probability p. That's the colored Kn that you get. From every monochromatic, for every red K3 you delete at least one vertex. From every green KL you delete at least one vertex. So both those deletions contribute to these two subtractions. Okay. Now I want you to, if you did not follow the details, I want you to pause and figure it out yourself. Ideally without doing any pen and paper work. Okay, I want you to figure this out in your mind. Next, let's see, we have two parameters to optimize. We want to tackle both p and n. Okay, so one thing should be clear, right? If you don't care about the constants, we are only looking for an omega kind of a lower bound. We know that using this method, the best you can get is n, or in fact some constant times, right? Because n minus something, so the best you can get is n. So it is okay even if the quantities that you are subtracting out is linear in n. If it's quadratic or if it's n log n kind of terms, you are lost. But as long as this is linear in n and that constant is less than 1, we are okay, right? So that's what I'm trying to claim. Okay, if you do not care about the constants, then it is enough to bound, let's say, this term by some epsilon 1n, this term by some epsilon 2n, such that epsilon plus epsilon 1 2 is strictly less than 1, maybe less than or equal to 0.9. Then this whole expression will be at least 0.19, and for order notations that is enough. Okay, so since it's not very easy to do a direct calculus here, we are going for these kind of approximate ideas. So so first we have to bound this guy. I'll pick this guy. Why? Because it's simpler, right? Yeah, it's simpler, right? So n choose 3. Was there a more? Yeah, it also gives you a function of p which only depends on n, and L does not come into picture here. So in order to bound this, it's a simple backward implication. N choose 3 is upper bounded by n cube by 6. Okay, n into n minus 1 into n minus 2 by 6, which is upper bounded by n cube by 6. You do all the cancellations and rearrangement. You will see that it is enough to choose p to be less than 6 epsilon 1 cube root, and this is the key thing that you have to remember, right? It would be n to the power minus 2/3. Okay, so now anyway, your epsilon 1 and epsilon 2 has freedom till 1. So to keep the expression simple, I am going to choose epsilon 1 to be 1 by 6. Okay, I am going to choose epsilon 1 to be 1 by 6. So you still have a room of strictly less than 5 by 6 for epsilon 2. I'm sorry, 5 by 6 for epsilon 2. So I am good. So this expression becomes simple, and you get this n to the power minus 2 by 3. But this now you remember. Okay, now you see that your probability is no longer a constant. It is not like 1 by 3 or 1 by 4 or something which we had in the earlier problem, the robot hat problem and all. We had a different P. It was also a non-uniform experiment, but there the probability was still a constant. But here the probability is a function of n, right? And it's a very falling function of n. How does this look like? This n to the power minus 2 by 3. It's 1 by n over 2 by 3. So this is a function when n equal to 0 power anything is I think 1, right? But then it will fall down drastically like this. Okay, I only have to bother about n equal to 1 because it's a, 1, 2, 3 will fall down drastically like this. So for larger and larger n, you are taking a smaller and smaller p. Okay. So that's one thing that I want to. So this you will see more and more frequently used later on. But there is nothing mathematically wrong here because for each n you are doing a separate experiment. So you can pick your p based on the n. Okay, so this ensures that this first term that you are subtracting out is at most 1/6 of n, or strictly less than 1/6 of n if you want. Now the second term also we need to be less than epsilon 2 of n, but again whenever you see this 1 minus p, right, 1 plus x we will always bound e to the power x, so it's enough to bound this and this n choose L. In order not to complicate, I mean I can bound it by something better like this, but this is also okay, n to the power n. Now that keeps the expression simple because anyway there is a lot of ugly calculation here. Take a natural logarithm here. What base of the logarithm would you generally pick? You will pick the base so that there is, if you see some exponent, that exponent becomes a good base. And when you see a base like e, it's natural to think about natural logarithm, right? So this would be L times ln of n minus p L choose 2, and this has to be less than ln of epsilon to n. Okay, so epsilon to n, I split it like this so that I can bring in the ln terms together. Ln, here is there is an L and there is a minus 1 which comes here. That's why there is a L minus 1. And this P, I substitute it with n to the power minus 2 by 3. That's what is happening here. And there is a Ln epsilon 2. Now, what did I do? Yeah, L choose 2. Yeah, this L choose 2 is L into L minus 1 by 2. So that I should have written more steps. That L minus 1 is what is coming out as common. So this L choose 2 is L into L minus 1 by 2. So that L by 2 stays here. The L minus 1 together with this L minus 1 has gone and sat as the denominator here. Okay. Now this guy is something which is of a, it's a nuisance. I would have rather liked this to be 0. Okay, then this whole expression could have been done easily. So since I am working with the implication backwards, it would have been okay if this expression was any positive number. In order for this bound to be satisfied, it was enough. I could have easily replaced it with 0 and said that if this is less than 0. But epsilon 2, remember, is a number less than 1, and hence this is a negative quantity. Okay, so you want this to be less than some negative quantity, but it's not significantly negative. It's like remember we had choice till 1 by 5 or 5 by 6 or something, right? For epsilon 2 could be as large as 5 by 6 or smaller. But let's say even if I take epsilon 2 to be some 1 by e, then this would be some minus 1 by L minus 1, like very close to, and L minus 1 is large, right? So this is very close to 0. So I am happy as long as this first term here is even this is an overkill. Okay, this is just, even if this is more than this plus by 1, it's okay. Okay, but I'm going to ignore this plus 1 for a moment, and yeah. So but this still we have a distance to go. So I want this term to be slightly at least larger than ln n by 1. But that 1 I will ignore to keep the calculus simple. Now let us see what kind of n will make this work. Okay. Our natural choices, you have an L here. So in order to cancel that, what if I take n to be L to the power 3 by 2? So that this left hand side is 1. Okay, so that the left hand side is 1. But then what does your ln n become? Okay, I did not write the left hand side, right? But then ln n would become 3 by 2 ln of L to the power 3 by 2, which is 3 by 2 ln L. Okay, so that's not enough for us, right? This is just a constant 1, but right hand side is ln L, which will be growing, so this won't be met. Okay, so this is not enough. But now from that you might have got a clue. Okay, you have to kill this ln L. So I take something like L by ln L. Okay, and L by, why this 2 is there also, I did it first with, okay, maybe I'll do it here. Okay, what if I take n is equal to L by ln L to the power 3 by 2, then what happens to the left hand side? The left hand side is n to the power minus 2 by 3. So minus 2 by 3 here will leave a minus 1. L by ln L to the power minus 1, which is ln L by L, and multiplied with this L that is there. So it will be an ln L. What will be RHS? RHS is ln of this n, which is 3 by 2 ln L minus ln L. Okay, but again you see that the RHS is larger by because of this 1.5 3 by 2 factor here. Okay, that's because of the 3 by 2 factor here. So in order to kill that, if you now add a slightly smaller n, remember our idea was to find the largest n possible, but we have to sacrifice this for the denominator. Okay, then there would be a 2l here, so LHS is only half of ln L, and when you take a log 3 by 2l minus ln 2 ln L, okay, I mean these are minor quantities, or this would be another minus ln 2, which is a constant. So this is half ln L versus 3 by 2 ln L. So this RHS is now going to be larger. Okay, so this choice of n is enough, right? But again, we are not really bothered about this 2 to the power 3 by 2 or anything, because we are only working at the omega notation kind of thing. But the expression is L over ln L to the power 3 by 2, and that is what we claimed we will show. Oh, okay, this 3 by 2 had to be here. 3 by 2. Okay, yeah, so yeah, in these cases actually here the normal union bound or expectation technique is harder to do. This optimizing this beta, if you see, it might fall back very well. Okay, yeah, so next class also we will see one more application of alteration method, but that would probably take a full class, and yeah, that's for the next class. Thank you.